Yes.
Okay, I'm going to get started in the interest of time. Today is going to be a little bit different. We're not going to have a discussion. We're going to do that on Blackboard. So I'll send out an announcement to remind everybody, but you'll just submit your write-up on Blackboard and then respond to your peers through that means. Then I'll be on Blackboard as well, responding to you guys that way. And then we're going to end early today. So we'll go through the hypothesis testing material, and then I will do homework help also on Sunday at some time so that you guys can jump on Sunday if you need some extra time with me. So, okay, so that said, let's get started. And I am in my office in DC, so if you see things going on in the background, that's what's happening. Okay, so this week we're talking about hypothesis testing. In your book, if you did your reading this week, it's kind of the final piece to the last 3 weeks that we've been talking about how to calculate different ways of testing for means or proportions, confidence intervals, and so on. So let's go to our slides. All right. So we're going to do our hypothesis testing, take a break if we need it, and then wrap up. And I expect that we will be done in probably actually less than 2 hours. So this will be a short week, and then we've already gone over in other weeks, and then we'll do our discussion online, like I said, and homework help on Sunday. So, okay, and this week is pretty straightforward. We're kind of hammering home concepts from before and talking about confidence intervals again. This is just another way of doing a randomized experiment and then seeing if your results are significant. So the concepts that we learned this week will play into next week's material really nicely. Next week, we're going to be talking about regression analysis. So we need to understand what it means to reject a null hypothesis and to have a statistically significant test statistic. So in hypothesis testing, we're collecting sample data and we're checking to see whether or not we have enough evidence to support some theory. So our hypothesis that we're trying to prove is called our alternative hypothesis. And it's on us to reject the null hypothesis, which is generally the status quo. It's what's the current thinking is. So it's what we're trying to disprove, basically. All right, so there are a couple of concepts that are really important in this chapter, and we're going to go over those. We're going to focus a lot more on the first half of the chapter because it's what's critical for you all. And then when we walk through the examples in the last part of the chapter, the text gets a little mathy. I want you to understand like how these concepts are applied. I don't want you to worry about the formulas. Again, there are templates this week, so we would be plugging in information into the templates. So knowing which test to use, but not how to do the calculations, and then how to interpret the test results. So let's say we have a manager of a pepperoni pizza restaurant, and we're looking for a new method of baking pizzas. So we want to know if our new method is better than our old method, and we're going to just randomly pick 100 customers. Now, also note in real business, this is not really how we would go about this, but in order to illustrate how hypothesis testing works, we have to come up with some examples. So this isn't really a really good business practice, which I think the textbook touches on, but it's to help you visualize what this means. So we pick 100 people. We're going to send them their old pizza that they ordered, but also a new one. And we're going to ask them to try them both out and then rate the difference between the pizzas from -10 to 10, where -10 would be I really, really like the old pizza and I really dislike the new one. 0 would be they're both fine. And +10 would be I really, really, really favor the new one. So for hypothesis testing, we would say that the null hypothesis is that they're the same, that the new pizza is not better tasting. And our alternative hypothesis would be that the new method makes a better tasting pizza. So now we need to judge whether or not our alternative hypothesis is true. And we will use the mean rating over the entire customer population. So we'll call that mu, like we usually do for means. And we'll say if the mean rating is less than or equal to 0, then we would reject the alternative hypothesis and we would say that the null hypothesis is true, that the better tasting pizza is not any better than the older pizza. If the collective mean rating for the customer population is greater than 0, then we would say the alternative hypothesis is true and we can support evidence that the new method is better. There's some nomenclature here. The null hypothesis is labeled H sub 0, the alternative H sub A. You might see these other different ways of writing it, but basically we have two possibilities. They are non-overlapping sets. They are independent. Either the null hypothesis is true or the alternative hypothesis is true, but there's no, both of them are true or both of them are false. So it's an important distinction to make. Okay, so again, we're running tests to prove significance, just like we did last week. We have one-tailed and two-tailed tests. In the easiest way to think about this is a one-tailed alternative is we're supporting only evidence in one single direction. So one tail, one direction. Two-tailed is in either two directions. And we'll go through a couple of examples to highlight the difference. It makes it easier to kind of wrap your brain around. In this case, we only care whether the pizza for the new method is greater than the mean average rating for the old pizza. So we're doing a one-tailed test because all we care about is that new is better than old. We don't care if new is worse than old. If we wanted to prove that they were just different, better or worse, then we would do a two-tailed. But we only care about this one direction, that the new is better than the old. So that would be a one-tailed test. Generally, in business application, the book has a lot of one-tailed examples, but in business applications, usually we're doing two-tailed. So if you're really stuck and you're not sure, a two-tailed test is more conservative, so go with that if you really don't know which one to choose. Okay, so regardless of whether or not we decide to accept or reject the null hypothesis, it could still be the wrong decision. And you may have heard these terms in the medical field a lot, but they apply to all statistical testing as well. So if we incorrectly reject a null hypothesis when it's true, we call that a type 1 error. If we incorrectly accept a null hypothesis when it's false, we consider that a type 2 error. So the procedures that we're going to use to reject the null hypothesis, they favor caution. So we pick our test statistic based on type 1 errors. All that means is that we're forcing our situation such that we need really strong sample evidence to support the alternative hypothesis. So we're going to be really pretty confident that if we accept the alternative hypothesis as true, that we have very, very sufficient, good, strong, sufficient evidence. All right, so how do we do that? We need to prescribe the probability of a type 1 error that we are willing to tolerate. And the general significance level of this type of testing is alpha equals 0.05. And sometimes you might see 0.01 like we did last week. A larger alpha, such as 0.1 or 10%, that's a really large rejection region, and we're getting into a territory of our evidence is strong, but we would be more likely to have that type 1 error and probably not be comfortable with it. Okay, so if our sample results and all of our sample results in the rejection region are called statistically significant at this alpha level. So we're looking for this significance. So another approach is to avoid the use of the significance level and just report how significant the sample evidence is. So when we run these tests, we're calculating a p-value and we're comparing it to the alpha level. So so the p-value is the probability of seeing a random sample at least as extreme as the observed sample, given that the null hypothesis is true. And the smaller the p-value, the more evidence there is that we're favoring the alternative hypothesis. So we would say that sample evidence is statistically significant at the alpha level only if the p-value is less than alpha. And the advantage of this approach is you don't have to set a significance level ahead of time. And p-values are very easy to calculate, and any statistical software that you use is going to provide that information for you. Really quickly, we'll talk about type 2 errors. The type 2 errors are not generally part of the suite of tools that statisticians or analysts would use to assess the validity of this type of exercise. But we do, you can measure the amount of type 2 error, and we call that the power of a test. So it's 1 minus the probability of a type 2 error. And the best way to achieve high power on a test is to just increase the sample size. So the larger the sample size, the less likelihood that you would have a type 2 error in general. Okay, so the results of hypothesis tests are generally accompanied by confidence intervals, just like we've done before. And it gives us additional ways to look at our data and understand it. And for two-tailed tests, there's a more formal connection. When using a confidence interval to perform a two-tailed hypothesis test, we reject the null hypothesis if and only if the hypothesized value isn't inside a confidence interval for the parameter. So we'll see what that means when we get to the hands-on examples. In the case of the pizza, we would say we would want the confidence interval for the mean of the new pizza method. We would not want it to include 0 because we're trying to prove that the mean is greater than 0. So if we get the mean of the new pizza is 3 plus or minus 4, that means our confidence interval goes from -1 to 7, which includes 0, and 0 is the parameter for our null hypothesis. So we actually don't have a very strong, we would question the results of that test since the null hypothesis is included in that confidence interval. Okay, so let's talk about hypothesis testing for population mean. So if we subtract the true mean from the sample mean and we divide the difference by the standard error, we get a t-distribution, just like we talked about last week, and it has n-1 degrees of freedom. In hypothesis testing, the true mean that we use is the null hypothesis value, and we label that mu sub 0. So to run the test, or the t-test for population mean, we would calculate the test statistic, which Excel does for us. And if we did that for our pizza ratings, here's what it would look like. This is not the right, 1 second. Okay, pizza ratings. Okay, so here's our data that we collected for our 40 people. Here's the hypothesis testing for population mean. Remember, we're trying to show that the mean of the new pizza is greater than 0. So we're doing a one-tailed test. The hypothesized mean is 0. This is what we want it to be greater than. We take our sample size. Again, we're using formulas as much as we can with data ranges, because if we want to add data or change any of the data, all of our formulas will update automatically. If we hand enter data, we don't get the same flexibility. So if we input the mean and the standard deviation, which are just calculated from the average and the standard deviation formulas or functions, then we can calculate the standard error, which means we can calculate the test statistic. And this is just the formula that we talked about in the book. And then there's our degrees of freedom, and we use all of that information to calculate the p-value. I do not worry about that formula, just use the template and let it calculate it for you. So in this case, our sample mean was 2.1, which is good, it's greater than 0. And our p-value is 0.004. That's a nice low p-value. We can support evidence to reject the null hypothesis. We can say, yes, there's clearly a preference with your customers for the new pizza. So that's exactly how we would interpret these results. This test statistic is telling you that you are about 2.8 standard deviations out. So that also just gives you another thing to look at. That's pretty good. That kind of helps support the low p-value. Okay, back to our slideshow. Okay, so like I was saying, that t-value is telling you that the sample mean is about 2.8 standard errors to the right of the null value. So pretty strong evidence. If we changed the alternative and rephrased it, the results wouldn't really change. And I don't know why they point that out, but they felt like you needed to know that. So let's say instead of deciding whether or not one is better, the pizza manager just wants to decide if they're different. So in this case, we just want to know that the two means are not the same. And so we would, that would mean the new style could be either better than or worse than the old style. In this case, we would do a two-tailed test. So the t statistic is the same, but what happens is basically the p-value doubles. And so because this is a stricter criteria, and if we double that, if it was 0.004, so it becomes 0.008, it's still less than 0.01. So we can still feel pretty confident that the mean ratings for the two pizzas are not the same. So just like we did confidence intervals for a wide variety of parameters last week, if you remember, we did proportion of population, difference between two means. We can do the same thing here for hypothesis testing. So in each case, we're taking sample data, we're collecting a test statistic, we're assuming a normal sampling distribution, and then we calculate a corresponding p-value that measures the support for that alternative hypothesis. So let's talk about population proportions. So again, not stressing out about the formulas. The main point here is that if we're testing a population proportion P, then we have a sampling distribution that's approximately normal when our sample size is reasonably large. And we can calculate the distribution of the standardized value with this formula, and we'd say it's approximately normal with a mean of 0 and a standard deviation of 1. So since we're using standard normal, we have a z-test for a population proportion, where p sub 0 is the borderline value of p between the null and the alternative hypothesis. And in order to obtain the test statistic for the z-value, we would calculate it in that following formula, which Excel will do for us. So what does this look like in terms of business? Let's say we have a paper company an appliance company, and we want to see if our new process for responding to complaint letters results in an acceptably low proportion of unsatisfied customers. So currently, our proportion of unsatisfied customers after 30 days is 15% or 0.15. And we want to test whether or not the new proportion is less than 0.075. So notice the language, less than. We don't care about greater than or less than. We want only less than. That's all we care about. We're not concerned at all with the other side. So we're doing a one-tailed test. With the new process in place, we would track 400 letter writers, so our sample size is 400, and then we find that 23 of them are unsatisfied after 30 days. So 23 out of 400 is our proportion. So if you look at this here, we don't even need to open the spreadsheet. The alternative hypothesis is going to be one-tailed less than, and our hypothesized proportion is that it's less than 0.075. So if our sample size is 400 and our number with the property of interest is 23, our sample proportion is 23 out of 400, which is 0.058. Right off the bat, yes, that is less than 0.075, but is that a statistically significant result? So in other words, if we calculated the confidence intervals around the sample proportion, would 0.075 be included in that interval? And we'll actually calculate that later, but for now we just want to see if our p-value even holds up. So we calculate the standard error, and then we use the formula for the test statistic for the z-value, and we get negative 1.329, which is telling us that we're about 1.3 standard deviations to the left of our null. And so not as strong as the last example, and that checks out because our p-value is 0.092. Generally, we would reject this. We would say we can't confidently state that we've met our goal, that our alternative hypothesis is true. We're less than 0.075. Okay, we can also do hypothesis testing for the differences between population means. So this is a test that is done a lot. When I write papers on research, I generally am doing this testing for the difference between population means, which means, so for example, I wrote a paper analyzing flight data from a major outage in the Chicago airspace. It was a 2-week outage of the airspace of 30,000 feet and higher. So that's called the en route airspace. And what happens when there's an outage? Well, the initial outage was that a bunch of flights were diverted, canceled, or delayed. And then for the next 2 weeks, they had to route air traffic either at a lower altitude, which means the planes have to fly slower, or around the airspace entirely, so flight times were longer. So I wanted to know if the overall average flight time from the 2 weeks prior to the outage was different than the average flight time of the airspace, air traffic, commercial air traffic during the outage. And so to do that, we pair our samples, and then we do a t-test for the difference between means from the paired samples. So it's just a different way of calculating the t-value. And if our samples are independent, then we have these test statistics shown below. So the t-value, and where we're subtracting the means of each population from each other in that calculation. Again, Excel can handle all of this work for us. So if we want to apply this to a real example, we're looking at the effects of soft drink cans. We can use a paired sample t-test for differences between means to see whether customers rate how they're rating the attractiveness and their likeliness to purchase new style cans versus traditional style cans. So we would randomly select customers and ask them to rate on each of the following. So the attractiveness of the old can, attractiveness of the new can, likelihood of purchasing with the old style and with the new. So I think their things are attractiveness old, attractiveness new, will buy old, will buy new. I think that's what they were aiming for with those acronyms. So let's pull this up in Excel. Okay, so here's our data. We have each customer, and then we have their ratings, and then we have the differences between the ratings. The first thing they did was calculate, or they just drew up some histograms to kind of look at their data and how it's distributed. So these look pretty good. Then they also did some scatter plots between these different rating differences, just to kind of see if there might be any correlation between them. So I think here they're just showing you different ways to look at your data and visualize it. It's always good to do these types of exercises so you can start to see patterns in your data, things you might want to explore, so you're not wasting your time when you go to do your hypothesis testing. By looking at your data first, you can kind of point your analysis a little in a more targeted manner and avoid doing work that you don't need to do. So it's always good to kind of look at your data first. So if we look at the old minus the new attractiveness, we're doing two-tailed because we just want to know they're not the same. They're not zero. There's a difference in opinion between the two. So they just plugged in their information here. So their sample size, the mean, and the standard deviation. All of those are calculated very easily in Excel. Then we use the standard error formula, which, if you'll remember, is the sample standard deviation divided by the square root of the sample size. We used that last week. Then the test statistic is calculated from the formula in the book and the degrees of freedom. And from there, we can do our p-value test, which don't even look at that formula. It even stresses me out. So if we do that, and then we just copy over all of our formulas to calculate. So is there a difference in opinion between the attractiveness of the old and new? Looks like that's a pretty strong test statistic. It doesn't even register. We'd have to go out quite a ways. So that's a very small p-value. We can feel pretty good. There's definitely a difference in opinion between attractiveness. If we're looking at would they buy, the difference between would they buy the old and new, again, yes, there's a very strong difference in opinion. If we look at the difference in opinion, whether or not there's a difference between the means for how they rated the attractiveness and whether they would buy it, that checks out. Same with the attractiveness of the old and would they buy the old. What does not pass is this calculation here. So they took the attractiveness of the new and subtracted the rating for whether they would buy it. And then they subtracted the same thing for old and subtracted those from each other. And I don't have my textbook with me today, but if you go through the example in the textbook, they talk through why they chose this particular calculation. Let me see if I can, 693. I do have it online, so if you give me 1 second. Almost there. Okay. Okay, so they're measuring the difference, whether the translation of perceptions into sales is any different for the two styles of cans. So that's what that column J is supposed to represent. Okay, so from the output here, there's clearly overwhelming evidence across these three. And you can also look not just at the p-value, but look at how far away from the null these, in terms of standard deviations, these tests are. And then look at this one. It doesn't check out. So we could not accept the alternative hypothesis in this scenario. We don't have any evidence to support that there's a difference, the perception of into sales is any different for the two styles of cans. Let me see if there's anything else I want to say about this. Going back to the histograms really quickly. If you look at our histograms here, there are many more negative differences than positive differences. So that's how we get, and that's in this, in the first test here. So that's supporting the results that we got here, where, oops, where we got this negative t-value. Same for here. See, there's more negative than positive, just by eyeballing. For here, you can see that there's more positive than negative. Same here. So those all correlate to these calculations here. And then if we look at the histogram for the alternative hypothesis we can't support, that is not the case. It's pretty evenly distributed around 0. So that's just another way to illustrate that hypothesis testing and confidence intervals give us complementary information. Okay. Okay, so let's use a two-sample t-test to test for the difference between means between worker productivity of workers who exercise and workers who don't. So this company installed exercise equipment on site, and they want to know if it's making their employees more productive. So they gathered information from 80 employees. 23 use the facility regularly. 6 exercise elsewhere regularly, and then 51 don't exercise at all. So we're comparing 51 non-exercisers to 29 exercisers, and we want to know their supervisors rated their productivity on a scale of 1 to 25. Obviously not a perfect experiment because that could be a very subjective rating, but just for the sake of this, we'll pretend like there's no bias in the supervisors. So side-by-side box plots on the right. Looks like there's a difference between those who exercise and those who don't, but is it going to be significant statistically? Let's find out. Okay, so if we plug in all our calculations, when we're doing this for difference between means, we have more things going on, but don't let that intimidate you because you're still going to be using a template. So you need to understand where to put inputs, but you don't need to understand how to build out these calculations. So a one-tailed greater than hypothesis, because we're only concerned about whether or not the productivity for the exercisers is greater than the non-exercisers. And we're trying to determine whether or not that difference is greater than 0. All right, so our two categories are yes, we exercise, or no, we don't. If we do our count ifs on those criteria, we get 29 who exercise and 51 who don't. Then we can do these sample means for each population. So here's something to note. Just like we do this count if formula, we also have an average if formula. So in this case, we're saying take the average of the data for the productivity ratings if the criteria that they exercise equals yes. And then in this case, if the criteria that they exercise equals no. So in our data for that spreadsheet, we're saying check column B. If it says yes, include it in the average for exercisers. If it says no, include it in the average for non-exercisers. So when we do that, we get our sample mean difference of 2.725. So it's not zero, but is it significant? We need both standard deviations. So we can use, in this case, there's no standard deviation if formula, but they nested it. So they said, take the standard deviation of the sample, and then they nested a statement that says, if the data column for exercise says yes, then count it. Same thing for no, except they changed the criteria. So there's our standard deviations for each. So the average rating for exercisers had a standard deviation of 4, and there was more variability in the non-exercisers, which kind of makes sense, I guess. There's a formula for the pooled standard deviation and the standard error of the difference. Don't worry about those formulas. Excel does it for you. From that, we can calculate our test statistic. And from that, we can calculate the p-value. So if we plug in the inputs, everything else will fall in line very nicely. It will all calculate for us. This is a nice, strong p-value. So we could definitely accept that the exercisers are rated as more productive than the non-exercisers. Okay, can also do a hypothesis test for equal population variances. So the two sample procedure for a difference between population means depends on whether or not the population variances are equal. So it's not uncommon to test for equal variances first. And this test to do that is called the F-test for equality of two variances. And there's a test statistic for that. So the null hypothesis is that this ratio is 1, they're equal. So the sample variance for the population 1 and is divided by the sample variance for the population 2. Since they're the same, those equal 1. And or if the alternative then would be not 1. So we're if we're assuming that the population variances are equal, then the distribution associated with the test statistic, which is the F value, is the F distribution, and it has n minus 1 degrees of freedom for both both populations. So what does all that mean? In our previous example, they performed this test just to see the ratio is 0.6 and the p-value was 0.145. So the two population variances are not statistically different. Okay, we can also do, so we did a hypothesis testing for a population proportion. We can also do one for the difference between population proportions. So in that one example, we had the population proportion was 15%, and then we got the new population proportion was like 5.8% or something. So we could test to see if there's a statistical difference just between the two proportions themselves, as opposed to whether or not the new proportion was less than some value, which is what we did before. So the tests below are the formulas that are put into Excel to help calculate that. What does that look like? So we're at this Armco company now, and we're measuring employee empowerment. And we want to see if there's this program of accepting employee suggestions is appreciated by the employees. So this company has initiated a number of policies. They're responding to employee suggestions, but only at one plant. They did not put this process in place at their other plants. And they want to see if this has a lasting effect. So they took 100 employees from their plant where they, at the Midwest, where they and put this process improvement plan in place, and then 300 employees from the other plants. And they asked them to fill out a questionnaire 6 months after they implemented these new policies at the Midwest plant. So 2 specific items on the questionnaire were: management at this plant is responsive to employee suggestions for improvements in the manufacturing process, and management at this plant is more responsive to employee suggestions now than it used to be. So in our data, we'll look at, we have the results for those 2 items. They stacked them in side-by-side columns so that we wouldn't have to do 2 separate sheets. And so we have 2 categories, Midwest and other. So for each question, so the first question is column B, second question is column C. These are one-tailed tests because we're only concerned with whether the Midwest ratings are greater than the ratings of the other factories. So that's a one-tailed test, one direction, one tail. So the sample sizes are the same for both questions. That shouldn't surprise you. Then the property of interest. So we're calculating proportions again. So if we calculate those who responded one way versus everybody else, we get this 39 and 93. And then for the other question, it turned out to be 68 and 159. So now we have this proportion where 39% felt that they do respond, or I think, yeah. And then 31% 93 out of 3. Oh yeah, okay, so sorry. So the proportion at the Midwest plant is 39% said yes, management responds. The ratio of people who felt that management was responsive at the other plants was 31%. So they're different, but are they significantly different? We'll calculate out our test statistic and our p-values. And for management responsiveness, it's significant at the 0.07 level. So it's not as significant as we generally would like. We're usually aiming for 0.05 or less, but it's not bad. There might be something there. We would just have to, if we were briefing out these results, we would have to kind of note that that was the p-value. On the other question, have things improved? So 68% of the Midwest population felt that they had, and only 53% of the other plants without the new process in place. So if we calculate out all of our information for that, our p-value is really low. So we can definitely say that that process made employees feel as though things had improved at the Midwest plant much more strongly than no process at all. Okay, so we've been operating under this assumption that population data is normally distributed, which is an assumption that we have been making for the last 3 weeks. We can actually test this assumption, and to do that, we use a test for normality. So there's a couple of different tests for normality, and this is the part of the lecture where I'm going to break away from the text for a little bit, and just, we're going to talk about these tests, but I just want you to understand that there are a couple of methodologies for testing for normality, and not get too focused here on these equations that they use to calculate the chi-squared test statistic. So for the chi-square goodness of fit test, if we took a histogram of our sample data and we compared it to the expected bell-shaped histogram that we get if our data was normally distributed, then would they have the same mean and same standard deviation? We would kind of expect them to look very similar. So if they were sufficiently similar, then we would accept the null hypothesis of normality. So what does that look like? Let's say we have these metal strip widths and we want to see if they the widths are normally distributed. So they're supposed to have a width of 10 centimeters, but for quality control, you know, they're not going to be exactly 10. Some will be above and some will be below. So they're going to run some statistical tests. So they take 90 strips, they look at the sample data, they look at the histogram of widths. They look pretty good, pretty normally distributed. So to run the chi-square test, in this case, we would use the stat tools, and you could follow along in the book if you wanted to on your own time to try this out. But when you run the chi-square test from stat tools, you get an output that looks like this. And both of these, so note the high p-value. That's saying we basically accept the null hypothesis or we reject the alternative. And remember, the null hypothesis was normality, so we're accepting normality. So you can look at just the numbers and you can gather that this is normally distributed data, but you can also look at the bins here, the histogram here, and see that for this chi-square test, we're getting distribution from the widths that is basically what we would expect to see from normal data. So they look pretty similar. Another means for doing a test for normality is the Lilliefors test. This is a much more powerful test. It's based on what we call the cumulative distribution function, which shows us if the probability of being less than or equal to any particular value. So the Lilliefors test is comparing the cumulative distribution function from a normal distribution and the cumulative distribution function that corresponds to our data. And we're trying to see whether there's a fraction of observations that are less than or equal to any particular value. And if there's a large, and we'll when we look at this, you'll kind of see what this means. But if there's a large vertical distance between the two CDFs, then we would reject the hypothesis of normality. So what does that even mean? We can run Lilliefors using the stat tools normality test on our data. So we'd select our data and we just run it from the stat tools dropdown, and we get an output that looks like this, and we get this nice chart. And all this is it shows us the CDF of a normal distribution right here, the blue line, nice and smooth and pretty because that's our normal distribution. And then what does our data actually look like? So if we plotted our data's CDF, it looks pretty dang close. If our data was not normal, there would be a big the shape of the distribution would likely be the same, but it would be like, if you're following my mouse, it would be like up here. So there'd be a big gap in between. And actually, here, why don't I use my handy little tool? Okay, so instead of being basically in line with the blue, it might be like this. And this gap right here between the two, that's the vertical distance that we're looking for that would say, oh, actually your data is not normal. But in this case, it is. So that's a more powerful way of testing for normality. Finally, we can also do an informal test called a quantile plot. It's a scatter plot of the standardized values from the data set versus what we would expect if the data were perfectly normal. So the perfectly normal data would follow this red line right here. And the QQ plot, these are the actual values that we got. And you can see They follow pretty closely on this QQ plot. That's pretty good. You will always get this weird little funkiness toward the tails of your data, where it kind of like pops off more from the graph, because those tend to be like your outliers, or those are your values with the most error. So they deviate the farthest from the lines, and that's not uncommon for that to happen. But we kind of look at the overall shape of it. Is it following? Yeah, it looks pretty good. We can look at either of these examples and they all demonstrate in different ways normality. Another test we can do is a chi-square test for independence. And in this situation, we would want to know if a population that's categorized in two different ways, if their attributes are independent. So if we had people who are characterized by whether or not they smoke and whether or not they drink, we might want to see if those attributes for that population are independent. So meaning my drinking habits, or the drinking habits of anybody in the population, are of no predictive value when trying to assess their smoking habits. So the null hypothesis is that they are independent. Whether or not I smoke has no effect on whether or not I drink. They're not correlated at all. We would run the chi-square test for independence, and it would be based on the counts in like a contingency or a crosstab table. So if we set this up in Excel, and we're not going to do this for our homework, I just want you to see what these calculations look like and how we interpret them. So we're looking to see whether or not demand for Windows laptops is independent of demand for Mac laptops at this store. Are they related in any way? Meaning, if demand for Windows laptops increases, Mac laptops also increase, or it could go the other way. If demand for Windows laptops increases, does demand for Mac laptops decrease? So they could be inversely correlated as well. We just want to know if there's a relationship there. So they have daily information on their categories of demand. So they've classified demand as low, medium, high, or high. And when you look at this crosstab table, so these are days for 250 days. So 4 of the days demand for Windows and Mac laptops were both low. This is how you interpret this table. For 10 of the days, demand for Windows laptop was low, but Mac laptops was high. Conversely, on, let's see, 5 of the days, demand for Mac laptops was low, but was high for Windows laptops. So we're looking for, to use this data to figure out if there's a relationship between the two populations. So there's a test statistic for this. How it's calculated is not important. We just run the test statistic and use the degrees of freedom and the test statistic to calculate out the p-value. And in Excel, when they did this, the p-value was 0.045. So yeah, there seems to be a significance there. Okay, so if the alternative hypothesis of dependence is accepted, meaning that the demand, there is a relationship between the demand for Windows and Mac laptops, then we can calculate the percentage of row totals and column totals, and we would expect them to be the rows of the first table to be identical and the columns of the second table. And this is a little funky to look at, but let's actually go to, let me see if I can get you guys a better picture. 1 second. Sorry, this is not ideal. Okay, so all right, so if we look at these percentages a little more closely, what we're seeing is, so each row in the first table shows the distribution of Windows demand for a given category of Mac demand, and each column in the second table shows the distribution of Mac demand for a given category of Windows demand. So there's some evidence that there's some substitution going on, meaning when demand is high for one of them, then they just substitute with the other product, but it's not overwhelming evidence. And you can walk through, this is example 9.7. You can walk through it again in your textbook, but the point really is just that we can test for two attributes in a population to see if those attributes are independent. So that's it for hypothesis testing. This week is a lot easier than the last 2 weeks because we're just building on the same concepts that we've worked out the last 2 weeks. So we already know the concepts of our distributions. We understand what a t-distribution is. We understand normality. We understand confidence intervals already. So we're just building on that discussion, and that's why this week is not so intense in terms of lecture-wise. For your forum question, you were assigned, let me just make sure I'm in the right, yes, okay. You were assigned a little bit of research. So I gave you guys an article about machine learning and the data analytics lifecycle. And the first question is, why do you think that organizations are moving toward data-driven decision-making? You can, some of you have already started your responses, which is great. You're just ahead of the game. Just be sure to check back in and respond to your peers this weekend. So you can use real life examples if you'd like. You can use your own research. It's really up to you. The second part of this question is that the first letter of your last name, I want you to write up a paragraph following some of these best practices. So we're not gonna cover all of these in great detail, and some of you, well, just based on the small class size, we may end up not covering some of these at all. So I will give you this option as well. If you're reading your peers' responses and you see that some of these have already been covered and you want to cover one that no one's talked about, you don't have to base it on the first letter of your last name if you want to give the class some variety. So scientific method, CRISP-DM, which is very, very common in industry. This Delta framework methodology, the applied information economics approach, and MAD are the methodologies that we're gonna look at this week. And yeah, so instead of having our discussion today, this is actually much better suited for you guys to do this via the discussion board. So that's going to save us some of our class time today that we're not using, is because we're going to be active in our forum. So make sure your responses are well thought out. Make sure you're using your APA references, and then make sure that you're responding to your peers and in a thoughtful manner. So not just saying like great post, but actually asking questions or adding to theirs or tying in their write up with yours. All meaningful contributions. Okay, So that's that. For your assignment, we're working with some examples. The first couple of questions are conceptual. So you'll be using your reading from the book and what we talked about today. This first one should be pretty straightforward because we did a couple of 1- and 2-tailed tests. So you're just thinking through when it makes sense to use one over the other or when you shouldn't. And then the second question is asking about whether or not this scenario is an observational study or a controlled experiment. So again, there's some information in the textbook that will help you answer that question. 3, you actually get some data about a speed reading course, and you're trying to test whether or not they have can read faster on average. So that word average right there tells you you're dealing with a test for the population mean and before and after the course. So you're going to take the data, you're going to use the template for hypothesis testing, and let me make sure it's provided. Okay, I will send that out to you guys so that you don't have to plug in all of those formulas yourself. So you'll use the template, plug in your information, and then you're just interpreting the p-value and you're trying to come up with an answer. So it just acts as if you were reporting out on this information. Maybe you are in charge of this course and you have to prove its value to your manager. So you're using this data to support that your speed readers are actually reading faster. So in this case, is this a, who wants to chime in? Is this a 1-tailed test or is it going to be a 2-tailed test? Anyone? You guys with me?
Yeah, I'm here.
So would it be a 1-tailed?
I see you talking. Tyler, are you talking?
Yes, can you hear me?
I cannot hear you guys.
I can hear it, Tyler.
Hang on 1 second, you guys. Let me check something with the sound. Okay, can someone talk now?
Hello?
Okay, now I can hear you. Hey, Tyler, do you know if it's 1-tailed or 2-tailed?
So based on what it's asking, see if the speeds have increased on average as a result. Wouldn't that be a 1-tailed because you're only looking for one thing?
Yes,
Okay.
they're only concerned with the new scores being greater than the old scores.
Okay.
Perfect, awesome. Okay, and then for 4, there's a company, they're thinking about entering the golf ball market, and they will only make a profit if their market share is more than 20%. So if we're talking about their market share, what type of test are we talking about? Jackie, do you know?
No, I'm reading through it again.
So this is indicating this language is indicating a proportion. if we keep reading, it's saying 140 out of 624 will buy a golf ball. So we're looking at a proportion of the population and whether or not they will buy a golf ball. So they're saying this proportion needs to be greater than 20% in order for them to make a profit. So if you are working through this example and you feel a little stuck, go back to one of the earlier examples we did where we tested for the proportion. In that case, we were testing to see if remember the example was whether or not the proportion of unsatisfied customers was less than 7.5%. Now we want to test to see if the proportion of potential golf ball purchasers will be more than 20% for this brand. So also a one-tail test. So you're going to basically determine whether or not there's enough evidence to persuade them to enter the market. And then they're just kind of asking, if you were management, what would you do? Would you use this method or would you do something differently? So we had talked earlier on about how hypothesis testing is not super common in business practices. So just think about whether or not you think you'd go about it this way, or how you might assess market share, potential market share beyond hypothesis testing. So just to be extra clear, when we talk about like business applications for these types of tests that we've performed over the last couple of weeks, hypothesis testing, generally, we don't set out to create an experiment like this. We use hypothesis testing as analysts, at least in all of my experience, when we're doing like research, or we are looking at data and we're trying to assess whether or not our data supports some kind of evidence. So for me, what that looks like as an operations research analyst is when I'm looking at things like safety benefits, and I want to prove that some equipment or process is making air traffic safer. So I might look at the proportion of accidents prior to using, like equipping aircraft with some equipment, and then the proportion of accidents after, and then comparing the two proportions like we did in one of our examples. So that would be a time that we might use it, but that's a lot different from when we're setting out to do something like the pizza example, where I'm like, oh, I think this new way of doing pizza is better and I want to see if it's better. There are probably better methodologies for doing a random experiment and determining whether or not you're successful than setting up this sort of hypothesis testing scenario. But it's still important to understand the concepts, because like I said, all of these concepts, while the examples might be a little weird and they might not be the way that we probably would prefer to solve these kinds of problems, our next module is on regression. And so all of the things that we just talked about, like interpreting the p-value, understanding whether or not that a test result is statistically significant, is going to be important for doing our regression analysis work next week. And next week is really the first time that we get kind of hands-on and we start to look at like an actual analytics methodology that businesses use all the time. So that's pretty exciting, in my opinion. We've moved past all this core stuff and we're going to get into the practical applications for the next last couple weeks. The other thing I want to point out to you guys today, because I promised I would do this to, maybe it was Tashi, I can't remember who I was talking to, but I am going to make available your final project. So I'm making this available right now so I don't forget. Feel free to take a look at this. For your final project, you're going to be doing a case study. So I've given you a couple of resources, and you're going to choose a case study and download the data, and you're going to just perform some analysis on it. And let me see where it looks like there's actually something missing. So give me 1 second. That's your reading. Is it in here? Okay, good. When you click on that folder, it opens up your case studies that are available to you. So there's two. There's the stroke patient prediction. So according to the WHO, stroke is the second leading cause of death globally. And so you're getting a data set that is trying to predict whether or not a patient is likely to get a stroke. And if you're thinking like, how am I going to do this? Remember, we're just moving in next week to practical applications for analysis like regression. So while you can look at this data, it might be another week or two before you start thinking about ways where you can actually play with it. But if you want to get a head start, you don't want to cram this project all into the last week, the things you have learned to do so far are explore your data, do some descriptive analytics on it. So some histograms, looking at different attributes, correlations to see if any of the variables are correlated. So there are things you could do now, but just know that we're still building out this tool set. So you're not going to be able to do this project like right now, but you can certainly get started. And I've given you the attributes. So this has 12 columns. So the ID is just an identifier for the patient, the gender, so you get male, female, or other, age. There's some binary here. So hypertension, they either have it or they don't. Heart disease, whether or not they're married, their type of work, their average glucose level, their BMI, whether or not they smoked, and whether or not they had a stroke. Okay, so that's the first set of data, which is right here. The second set of data is student alcohol consumption. So they did a survey of students in math and Portuguese language courses, and they were trying to determine if you could predict the student's final grade based on all these things. So you get their sex, age, I mean, you know, some of these fields you might not need, you might want to just get rid of so they're not cluttering your spreadsheet. I can't foresee you guys using address unless you decide to go crazy and do some kind of geospatial analysis. Highly doubt it. Family size, which, and just note that, so when you look at the data, there's going to be LE3 or GT3, so either less than 3 or greater than 3. Parents cohabitation status. So there's a lot of variables in here. This data set's a little trickier because you have a lot of binary variables, yes, no variables. You have a lot of ratings, like how they spend their free time, the quality of their family relationships. So this could be interesting. You could try to see if any of those things correlate to their grades. Can you predict their grade based on this information? So I just wanted to show you guys that this is out there so that you can start looking at it if you would like. I'm also going to open up your module for next week because I always do that on Thursdays before, so that because some of you like to work ahead a little bit. And next week is only about linear regression. You don't have like a side discussion because it is a pretty big topic. So, okay. So do you guys have any questions about hypothesis testing or what we talked about this week?
Not yet.
Not yet. Okay, so let's do this. Like I said, I know we're done really early, but we're doing our discussion online, and we're doing homework help on Sunday. So yeah, this is just kind of a different way of doing a lot of the stuff we've been talking about the last couple of weeks. So there's just not a whole lot of new material. So read the textbook, go through the examples yourself. I will dig up a template and try to send that out, if not today, tomorrow. You could also just copy the way it is in the textbook examples give you the actual formulas. So you could always just copy those if you'd like, if you get impatient and you get tired of waiting for me. Since I'm on travel, I am a little more scatterbrained than usual. So if I don't send a template out by tomorrow, you are more than welcome to email me or text me and remind me. I will not be upset. I won't feel like you're micromanaging me. So if you're trying to get stuff done, it's okay to just ping me and remind me. Worst case scenario, I get it done on my flight home Saturday morning. So, okay.
I
You
did have
guys
a
get
quick question.
your afternoon back. Yes, Tyler, what's up?
So it's about the discussion board.
Yes.
So mine's the scientific method, and I mean that's I know it's a pretty broad one, but I did a little bit of research on mine, and I kind of found like the life cycle. It's kind of like formulate the question, generate hypothesis, gather, generate data, analyze data, draw a conclusion, and then communicate results, take action. That's kind of the right methodology that I'm looking at, correct?
Yeah.
Okay, I just wanted a kind of quick question on that one. So because there's tons of information on that one. I'm trying to condense it all, but I just want to make sure I'm on the right track. So.
Scientific method, it kind of cracks me up that it's in there because it's like it's like the first thing we all learn in grade school when we talk about like science and doing experiments and stuff is always like use the scientific method, and
Sure.
and it cracks me up because it's so ubiquitous. So that's an easy one to research for sure.
Yep. Okay, great. Thank you so much.
Any other questions, you guys?
Hi, Professor. So on the assignment, the case study, is it going to be individual or a group?
Individual.
Individual. Okay. Thank you.
Yep. I do not do group assignments because you guys are all busy individuals with jobs and lives, and it would be really cruel of me to try to make you guys try to find time where you can all get together. So I just noticed though, when I looked at that, it looks like when they copied over that module, they didn't copy over, and I have plenty of time to do this because I know you guys aren't going to be writing anything right now, but there should have been got more guidance on the actual paper itself, like the standard use APA formatting. It should have an introduction, it should have, or an abstract. So it looks like that's missing. So I will add that back in. I'll go dig it up and I will provide you guys with more guidance in the next week or two on the actual structure of the paper itself. But what you can expect to be doing is just looking at the data, providing information to me about the data. What is it? What's the spread for, so like if one of the variables is age, tell me more about that. Tell me what age range is my data? How is the age distributed? Is it pretty even across all ages, or is it a more elderly, like is it, you know, biased toward one direction? So give me a histogram, things like that. So you should be kind of thinking, oh, okay, looking at your variables, depending on which data set you choose, like what can you tell me about this data? Do the majority of the students live in large families or small families? So it's just, what am I looking at? So that's a part of it. Then I'm gonna ask you to use some of the methods to help try and figure that out. So in one case, you're looking for a correlation between stroke and different variables. And in another case, you're trying to predict grade, but they're kind of along the same vein. So we'll cover the methodologies for that, and you'll just talk about your methodologies, the things that you tried. And there's I think it's like 3 methodologies I want you to pick and try. And some of them may not really be successful, or they may not have great results, and that's okay. You just show me what happened and then what you got out of that. And then you'll summarize your findings. So you'll say, based on the stroke data, you can predict stroke by using these variables, and the result, like there's a significant difference between, you know, these 2 populations of whatever, however you ended up doing it. So we'll talk about this more as we get closer. I just wanted to provide that information for you guys early so that for those of you who plan out your weeks very carefully, you're not having to cram it all in at the last minute. So, and we had extra time today, so I thought I would start that dialogue. Hopefully it's not stressing you out. You'll be fine if you don't start it. I just wanted to, for those of you who are thinking ahead, I just wanted to let you know what's coming down the pipeline. Okay.
Okay, thank you.
Sure. Okay, enjoy your guys' afternoon. Hopefully getting out a bit early makes up for all the times I have kept you very late. And I will send out information about Sunday as well. Do you guys have a preference for a time of day?
Whatever works for you.
Usually I do it in the morning, so if that's good with you guys, I won't do it like super early. I'm not trying to make anybody get up early on a Sunday, but yeah, if you end up thinking like, oh, that really doesn't work for me, just shoot me an email, let me know. I'll settle in on a time in the next day or so and send out an announcement with that information.
Great. Thank you so much.
Thank you. Bye,
Thank
everyone.
you.
Thank you.
Bye. Have a nice day.